Right, thanks, Nick. I wanted to add that bit about my sponsored student days in the bio, just to show you all that I do have a little bit of railway heritage going back. I was a sponsored student and did a year off and did summer placements. I have fond memories of those times, but then I decided to continue with postgraduate study. Unfortunately, they didn't want to continue the relationship, so we went our separate ways, which was a pity. So I'm glad 25 years later to have an opportunity to give something back to the railway industry, hopefully. So I'd like to present to you a new design method that we've developed to help us incorporate the benefits of geogrids into the design of subballast and rail track foundations in a more realistic way. But it's a new design method that works with or without geogrid. So I'll be interested to hear your feedback. In particular, if you are interested in the method, we'd be very interested in any sort of pilot studies, if we can do any validation of the method. That's always something very difficult to do with new rail design methods, is get the opportunity to do some validation. So we'd be very interested to hear from you if you know of any opportunities. So moving straight on, it's a development of the Lee-Selig design method. So a lot of you I expect will be aware of that method. That's the current state of the art regarding rail track foundation design methods, but it's not used a lot in practice. It's quite difficult to use. But the idea of the method is to prevent two types of subgrade failure. So that's the progressive shear failure you see at the top, leading eventually to heave at the shoulder, and also excessive plastic deformation. So that's the formation of ballast pockets, which of course they create their own maintenance headaches as water collects in those ballast pockets. So the design method is intended to prevent those by making the thickness of the ballast and subballast layers sufficiently high that we do not get these failure mechanisms developing during the design life of the track. So it's a performance-based design method in that rather than just a simple bearing capacity or stiffness, it actually predicts the accumulation of that deformation during repetitions of loading. And it's all based around this fundamental relationship for the development of permanent or plastic strain in the subgrade. It's equal to A times the number of repetitions of an axle load. So traffic tonnage can be converted into an equivalent passage of a group of 4 axles. So that's N, the number of repetitions of the loading, raised to the power B. So quite a simple equation behind it, but it's quite a task to derive particularly that A parameter. Now, mathematically, the definition of A is just epsilon P on the first loading, because when N equals 1, epsilon P equals A. So you need to predict what is the plastic strain in the subgrade on the very first time it gets loaded. And then N to the power B adds the accumulation due to repetitions of that loading. So the B is relatively straightforward to determine. It's just based on soil types. So there's not much difficulty there. The challenge comes in this A parameter. And this is where the method gets rather empirical. So there's another equation to try and derive that capital A parameter. So we have these empirical values. A and M depend on the soil type. Even the authors themselves admit that on the lowercase a parameter, there's a lot of uncertainty in that parameter. The soil state, that's called, that's represented by a soil strength parameter. And then the deviatoric stress, so this is the effect of the loading on the subgrade, that's determined using elastic layer analysis, quite an old analysis method using GeoTrack developed back in 1980. So that is to predict the accumulation of plastic strain. Then there's also deformation as well, and that's done by integrating the plastic strain over the thickness of the subgrade layer, as shown there. And that H value there, that is what is being determined. So the softer the subgrade, the higher the load, the bigger H needs to be to prevent those failure mechanisms occurring during the life of the track. So here comes the development of that. So we've taken Lee-Selig, But instead of using that rather unreliable empirical process to predict the parameter A, how about using FEA, finite element analysis? Elastoplastic constitutive models that predict plastic deformation have been around for many years and are used routinely in geotechnical engineering. So why don't we introduce it to rail engineering? So that's the step forward with this method, is using FEA and advanced elastoplastic constitutive models that are used. They're complicated, but they're used relatively routinely in geotechnical design to predict that tricky A parameter, and then for the accumulation of deformation, use that more reliable and easier B parameter. So the purpose of the FEA is to predict the deformation on the first loading. So we need a bit of validation for this. So we've got some laboratory testing. So this was done at the Technical University of Prague. It's half a sleeper in a ballast box overlying a subgrade of mixed material, silt, clay, and sand. It's a 300 millimeter thick ballast layer, this one. There were some other tests with a sub-ballast layer as well. It was loaded, cycling from 2 to 76 kilonewtons for 500,000 cycles. The distinguishing feature of the test are those yellow tubes. They are displacement transducers measuring the deformation at the subgrade. That's quite unusual in this testing, but that is what you need really to validate the method, because that's what it's trying to predict. So during the cycling, it was measuring the deformation in the subgrade. And there are some results there. The dots are the laboratory data, and you see they fit that equation I showed at the start, this time in terms of settlement. So 0.4 and 0.8 are the values where it crosses here. So one cycle. But it's important to stress that this parameter is not something we would physically measure. If you just apply one load and then try to measure a tiny displacement, it's not going to work because you've got bedding in effects and things like that. So remember, it's a curve-fitting parameter. But in the idealized world of FEA, it's possible to predict a parameter such as that. But you notice that the fit to the data is about the whole curve. It isn't trying to fit this. We didn't even measure it here. It was, the first measurement was taken at 100 cycles. But the line is defined by these equations. So you see they fit the data very well, with a B value of 0.12, which is appropriate for that mixed material subgrade. So to validate the approach, we back-analyze those tests. So that's a 3D FEA model setup of the ballast box. We apply one load and release and look at the permanent deformation that is left at the subgrade surface. And those four crosses are the locations of the displacement transducers. So we get 0.7 millimeters without the geogrid in place, and we get 0.3 millimeters with the geogrid in place. Those are very close to the 0.8 and 0.4 that you saw on the previous graph. So that's our validation based on the laboratory testing. And then multiplying it by n to the power b got us a good fit with the accumulation. Right, let's scale it up now to real-sized. So we back-analyzed the low-track modulus trials at the Pueblo site in the US as one of the few test sites that that have looked at this issue, deformation of subgrades. So we set that up in a 3D FEA model of the whole test using planes of symmetry. That's why there's only half a track there, and there's also only half a track in the long direction. It's just two axles, and there are two of the same axles on this side of the analysis as well. So there are all the layers. I don't need to go into all that detail. It's just replicating the low-track modulus trials. But the procedure is apply the wheel loads that you see with the blue arrows and then release the load, and the subgrade permanent deformation is predicted by the constitutive model that we use there. So the reason this subgrade appears to be in a box is that's how the trials were done. It's naturally a silty sand in that area, so they dug out and constructed a clay subgrade. There were 3 trials done, one called the TLTM, that was sort of an initial trial, and then they did 2 phases. They didn't actually measure subgrade deformation. It shows that even in a dedicated test, because it's difficult to do, it isn't often measured, so the performance was measured sort of qualitatively, and you can compare in the quotes, the relative performance of each of those cases. So this one had a higher strength, SU of 83. They decided to use a lower strength in the following trials, and you see that the total thickness of the ballast layers varied like this as well. This was the best performing, this was the worst performing, and this was somewhere in between. So we're looking for relative differences in performance. The P is the wheel load enhanced for dynamic effects. So that's something that we haven't looked at, but you can choose how to include the effects of the dynamic effects into the load. So when we do the analysis, we get this output. Under a single loading, plastic strains of that percent, and we get permanent deformations of those values. Then we can multiply them up by n to the power b, taking b as 0.18, and we look at the relative performance compared to the design criteria in the original Lee-Selig design. So relatively speaking, this is a good validation of these techniques. This one performed very well and is well below the performance criterion, whereas these 2 essentially failed and they exceeded the criterion for plastic strain and just about exceeded it for deformation. So we've got the best level of validation that we can get on a full-scale trial. So now that we've got a validated model, that can be used in design. So you can choose to do it by FEA. But we also wanted a more straightforward method that was quicker than doing 3D FEA. So to help facilitate that, we did quite a large parametric study and sensitivity analysis. So I'm not going to go through all those parameters, but we tried to cover the whole range of all the different parameters that you can get, and we looked at the output that is obtained. So we plotted it here. This is subgrade strain. So for all those cases that you saw on the previous slide, we plotted all those, the plastic strain that we get on the first pass in the subgrade. And we've got an interesting relationship by plotting that against mobilized strength in the subgrade. So mobilized strength is simply the deviatoric stress at the subgrade, the maximum value, divided by 2 times the undrained shear strength. So when it's 1, it's failure. Any fraction of that is partial mobilization of strength. So from 0 up to 1, we get an increase, quite a clear hyperbolic relationship as shown by the second equation to predict the permanent deformation or the permanent strain based on mobilized strength. So that was an interesting relationship that could be used in more basic design methods. Now, of course, there needs to be a threshold. If you go above a threshold, then subgrade deformations start to accelerate and you get to failure. The old British Railways method was a threshold stress method, generally thought of as being overly conservative. That's because the threshold was at about 50% of strength. If we use an alternative definition of a threshold stress out of University of Nottingham based on a 1% strain after 1,000 passes, then we get a threshold that's of about 0.65 instead of 0.5 like the old British Railways method. That seems to work better. So all designs would need to be below this threshold level. Now, could we do this? How could we calculate MS instead of by FEA? If we could find a straightforward way of calculating MS, the mobilization, the strength mobilization, we could then predict this strain in the subgrade quite straightforwardly. So that was the next task, to try and produce a simpler design method. So to do that, we need to find out what the equivalent sleeper pressure is below there. So we need to find an equivalent wheel load. No matter where the wheel is positioned, what is the equivalent load? So the main factor is rail stiffness. That affects how much the wheel load is distributed between sleepers. So we developed some relationships based on that that I'd love to go into more detail on, but we're restricted on time. But using the FEA parametric study, we derived some quite useful relationships between those parameters. Also, the effect of axle spacing compared to sleeper spacing. So sleeper spacing is S, and we have the axle spacing in terms of sleeper spacing. So that's for adding adjacent loads. So we derived just this simple equation there to calculate Qmax. So the maximum deviatoric stress using something similar to a Boussinesque relationship. So that's the factor on the wheel load, depending on how much is actually distributed down the main sleeper. The P is the wheel load. Those are the sleeper dimensions. That's the thickness of the ballast. That's the width of the sleeper. So a very simple equation. So if we calculate MS using this method, we plotted the results on here, and they look almost identical to the FEA output. So all that complicated FEA elastoplastic analysis, that's all validated, but in the end, once you've done that hard work, you can find a pretty quick method for doing rapidly different options for the thickness of your subballast layers. So as long as we stay below this threshold level where the results start to drift off due to yielding, we can predict, using this simple hyperbolic relationship, the permanent strain in the subgrade. And then we just multiply it up by n to the power b for the number of repetitions of the load. We've done the same thing for subgrade displacement. That's based on mobilized bearing capacity as opposed to mobilized subgrade strength. No time to present that now, but it works in a very similar way. So we can predict both the subgrade permanent strain to avoid the heave at the shoulder, and also the permanent deformation to prevent ballast pockets. So to summarize, using 3D FEA, we've developed a new performance-based track foundation design method. It's a development on the Lee-Selig method. It's validated by the low track modulus case studies in Pueblo. We can then introduce, using this method in a more accurate way than existing design methods, the benefits of mechanical stabilization of subballast using our GeoGrid products. So you get improved performance, or you can have thinner subballast layers and so save money on the construction projects. It's also validated with GeoGrid by the ballast box testing, but we welcome opportunities to do some full-scale validation. You can choose to do the design by FEA, or we've developed a simple strength mobilization method that can be used for rapid optioneering, or if you consider it reliable enough, could be used in actual designs. Regarding implementation of it, at the moment we have it in our own internal design spreadsheets, so we can produce designs. We have done a number of designs already as proposals. One actually got installed in Sydney in Australia, so we've done the first actual application with this. We are going to develop a design web app soon, so look out for that. So you'll be able to do your own designs by this new method. And we have a journal paper undergoing review at the moment, so hopefully that will be published soon, and you'll be able to review the method in detail. So if you're interested any further, then please do get in contact with me or anybody else at Tensar, and we could talk further about the design method and maybe bringing some savings with our applications. Just to finish with, just want to put in a plug for our own symposium, if you don't mind. It's free of charge. We've managed to attract a good panel of speakers from across certainly the Eastern Hemisphere, right from Australia, including China, Prague, SNCF France, Levente, who many of you must know at Network Rail, and Professor William Parry. He will deliver his Proctor lecture that was given recently at Transport Geotechnics Conference. contact anyone at Tensar, or you can contact Michelle Lee in the marketing department to find out more about that. Okay, thank you very much for your attention. That's all.